সো কন্টিনিউইং আওয়ার ডিসকাশন অন মাইকেল রিয়াকশান, যেটা আমরা আগের দিন পার্টলি ডিসকাস করেছিলাম। কিছু টেকনিক্স আমরা বলছিলাম যেগুলো সো কল্ড কনভেনশনাল মেথডকে সারপ্লাস করেছে এবং বেটার রেজাল্টস পাওয়া যাচ্ছে। তারই একটা ভার্সন হচ্ছে সলিড স্টেট রিয়াকশান। সলিড স্টেট রিয়াকশানের সবথেকে বড় অ্যাডভান্টেজ হচ্ছে যে সেখানে কোনো সলভেন্ট লাগে না, তার ফলে এনভায়রনমেন্টালি হ্যাজার্ডাস সলভেন্টের ডিসপোজালের কোনো প্রবলেম নেই এবং রিসোর্স কম খরচ হয়। তো এই কম্পাউন্ডটা বানিয়েছে, এটা বেসিক্যালি একটা জ্যাসমোনের সঙ্গে খানিকটা এর মিল আছে। এর নাম হচ্ছে অ্যালাইল রেথ্রন। এটা একটা পাইরিথ্রয়েড ইনসেকটিসাইড ক্লাসের একটা ইম্পর্ট্যান্ট কম্পোনেন্ট। এইটা বানানোর জন্য ওরা রবিনসন অ্যানুলেশন ব্যবহার করেছে। রবিনসন অ্যানুলেশনটা কোন দুটো রিয়াকশনের কম্বিনেশন? কোন দুটো রিয়াকশন কম্বাইন করে রবিনসন অ্যানুলেশন হয়? মাইকেল
আর অ্যালডোল
ফলোড বাই অ্যালডল। ঠিক, প্রথমে মাইকেল হবে, তারপরে অ্যালডল হবে। So they have done this Robinson annulation to access this allyl rethron. So they have started from a nitro compound. So this is an enolate source from nitro, and this is methyl vinyl ketone. This is the Michael donor and this is the Michael acceptor. Anion here and it attacks here and it goes there and it goes there and then comes back and gets a proton from the reaction medium. দেখো Al2O3 catalyst হিসেবে ইউজ করা আছে। So this is the new carbon-carbon bond. Clear? Okay. Now after formation of this particular Michael adduct, they have converted this nitro into carbonyl. Can you tell me a method, at least the name of a method through which this transformation can be done? একটা এক্সাম্পল দিতে পারবে? বলো। ম্যাকমারি, কারেক্ট। অ্যাকুয়াস TiCl3 দিয়ে করে ম্যাকমারি রিয়াকশন। তারও আগে আরেকটা রিয়াকশন করতো, দ্যাট ওয়াজ নোন অ্যাজ নেফ কার্বনিল। রাইট, কারেক্ট। নেফ কার্বনিলের রিয়েজেন্টটা কী ছিল? হোয়াট ওয়াজ দ্য রিয়েজেন্ট অফ নেফ কার্বনিল? So you basically deprotonate the alpha proton of the nitro, so you get the nitronate and then you acidify it so that you can get the carbonyl compound. Here they have done in a similar way, but the oxidation reaction has been done with H2O2. So this has converted the nitro into the carbonyl, and this is a very important method because this gives rise to an acyl anion equivalent. Like if you have RCH2NO2 and then you can generate an anion on the carbon because nitro is -I-R, and after some sort of introduction of an electrophile at that carbon, you can convert the nitro into carbonyl, then it's like basically an acyl anion. And we have talked about that in some details in our semester 4 class, as far as I recall, when we were discussing Ampolong reactivity and organic synthesis. Now they have ended up with this diketo compound and they have treated it with alkali. What is the reaction? এটা কি হচ্ছে? কি রিয়াকশন এটা? এটা কি রিয়াকশন গো? এই রিয়াকশনটা কি রিয়াকশন? অ্যালডল না? ইন্ট্রামলিকিউলার অ্যালডল, রাইট? এখানে মাইনাস হলো, দিস অ্যাটাক্স হিয়ার, দিস গোজ দেয়ার, and then eventually the alkoxide gets protonated and eliminated via U1CB reaction, so you get the allyl rethron. So this is a solid phase reaction. At least the Michael reaction is done in solid phase. After that you are doing a solution phase reaction, but the Michael reaction is done in solid phase. Let's move on to the second example. Now these are chalcone derivatives, okay, where you have alpha beta unsaturated carbonyl, and you also have at the carbonyl carbon you have an aromatic ring. At the beta carbon you also have some aromatic rings. This R can stand for hydrogen or chlorine or bromine. They are just grinding this in a solid state and doing a intramolecular aldol intramolecular Michael reaction, where the OH part is acting as the Michael donor and it is attacking this carbon, and the ring is being closed, and this part is acting as the Michael acceptor. So we are ending up with a template which are known as flavones. Okay, these are found in plants and they are effective antioxidants. So flavone or flavonone rich diets are recommended to prevent aging. Synthetically they can be prepared in many different ways. One of this is highlighted here. বোঝা গেছে ব্যাপারটা কি হলো? রিয়াকশনটা বুঝেছো কি হলো? এগোই। এবার as usual they will ask you what is so green about it. So I have told you before that the reaction occurs under solvent free condition. That's good because you don't have to dispose of the environmentally hazardous solvents. Condensation products are obtained in better yield. That means the side products are not formed. Michael reactions are always run with the risk of some sort of side product. Polymerization can be a problem, as we have discussed, and the reaction can be done even at room temperature in many cases. So those are energy efficient conditions as well. Moving on to a reaction where we are doing the Michael reaction in presence of surfactants such as hexadecyl trimethyl ammonium bromide. These reactions are done in water, and surfactant provides a hydrophobic environment where the reacting molecules can gather and can combine with one another. This alpha beta unsaturated carbonyl compound, this should not be water soluble, at least not very much, because it has the hydrogen bond acceptor carbonyl, but also it has large hydrophobic parts. Therefore water should not be an ideal solvent for it. Reactions with this substrate should ideally be carried out in organic solvents. However, if I want to avoid the use of organic solvents on the ground that they are not sustainable solvents or they are not green enough, then I can use surfactants which are inside water. They can provide hydrophobic interior where this molecule can take refuge and make reaction with some sort of reagents. So they have done this. They have used this compound as the Michael acceptor and secondary amine such as dibutylamine as the Michael donor. Can you see the Michael adduct? What has happened? Yes. Nitrogen lone pair attacks here, no? And then subsequently goes on whatever happens there, right? So in water, within 2 hours it gave like 98% yield. Fine, okay. This compound is powdered and suspended in water, and then the whatever surfactant you are using, it is added, and the reaction proceeds. What is the name of this compound? এটার নাম কি? এর নাম কি? হ্যাঁ, once again, ethyl acetate. How can it be ethyl acetate? This is the you know the ethyl version of this compound, no? If it is ET, what do you call it?
Ethyl acetate.
So what is the name of this one?
Methyl
This is methyl acetoacetate. So I mean, they have taken this example from the literature. So if you ask me that will this reaction not work if I take ethyl acetoacetate, I think it will work. But the literature says they have done this reaction with methyl acetoacetate. Maybe the yield will be not as great as 98%, but with ethyl acetoacetate it should also work. So this is the Michael donor, and that again the chalcone is again the Michael acceptor, and this is the new carbon-carbon bond that is being formed. Additionally, they have used a base here, potassium carbonate, which acts as the proton abstractor, and we get 98% yield in aqueous medium using surfactant. So that's good. Another Michael donor is thiophenol. Sulfur is what? Soft or hard compared to oxygen, let's say. Is it softer or harder?
Softer.
It is softer, much softer. Sulfur's nucleophilicity is actually better than that of oxygen, not only because it is less electronegative and more willing to part with its electron pair, but also because sulfur is more polarizable because of the larger size and the associated loose electron density. It is more polarizable, and therefore it is a softer kind of nucleophile. And remember from our previous discussions in semester 3, semester 4 as well as semester 5 that for Michael reactions we are actually looking for softer nucleophiles. So thio based nucleophiles, sulfur based nucleophiles are like ideal nucleophiles for this type of reactions. So this reaction is happening with say 92% yield in surfactant, where potassium carbonate is again being used as a base. In aqueous medium you are getting this compound where this is the Michael donor and it is attacking here, and etc., so on and so forth. Anything confusing about these reactions?
No, sir.
Okay, so just remember the chalcone structure, and if you forget about methyl acetoacetate, if you write ethyl acetoacetate, I don't think that they will come after you and deduct any marks in your exams. But obviously you can also remember by remembering that sulfur is better than oxygen as far as nucleophilicity is concerned, and it's also softer, so PHSH, maybe that will be ringing a bell to you. Let's move on to the green context. What's so green about this? The presence of the surfactant, as I told you, allows you to do the reaction in aqueous medium. So that's a green solvent. That's a huge benefit, huge plus point. The surfactant that you are using is sequestering or isolating the reactants, the chalcones, as well as the Michael acceptor, as well as the Michael donor nucleophile, soft nucleophile, inside its inside the hydrophobic environment that it provides even in the aqueous medium. In pure bulk water there is no hydrophobic environment, but in presence of surfactants you have a hydrophobic cocoon where you can sequester these reagents, and by doing so you are artificially increasing the concentration of the reactants as well as the reagents, and therefore the rate of the reaction is actually significantly increasing, and thereby reducing the reaction time, and the yield is very good for this type of reactions. And the Michael retrogression or the abnormal Michael reaction, which is sometimes a menace as far as Michael additions are concerned, those are minimized here. So would you be able to write quite a few of these points if they ask you to write this thing? লিখতে পারবে তো?
Yes, sir.
Okay. Okay, just remember for Michael there is a retro Michael or abnormal Michael reaction, so you write that point as well, that under this condition the abnormal Michael products are also minimized. Okay, then moving on to the microwave irradiation, using microwave irradiation as a energy efficient technique to impart some green or sustainable character for our Michael reaction. So this time we have taken 2-phenyl cyclohexanone, and this is an interesting molecule Which one of the hydrogens of this compound is most acidic, do you think? Which hydrogen is most acidic? Is it any hydrogen on this phenyl ring, or any hydrogen on this cyclohexyl moiety? Which hydrogen is most acidic?
Ortho 2 carbonyl
We don't call alpha 2 carbonyl is acceptable, ortho 2 carbonyl is not acceptable. When you say ortho, you are basically meaning aromatic rings. So if you think in terms of the phenyl, then you can use the terminology ortho, meta, para, etc. Alpha 2 carbonyl should be like more acidic, but are the two alpha carbons equivalent? Are the two alpha carbons equivalent? Are the two alpha carbons equivalent here? This one is one alpha carbon, this one is another alpha carbon. So we have one hydrogen here and we have couple of hydrogens there. So which one do you think is more acidic? On which side? This is easy, actually, very easy. Think in terms of the this one. Let's call this 1 and let's call this 2. Hydrogen 1 or hydrogen 2?
Hydrogen 1.
Why?
Hydrogen 2 phenyl plus or effect.
No, think in terms of what happens if you place a minus charge here. Phenyl can exert pulsar effect when it has a neighboring positive charge, but phenyl can also delocalize electron density. Yeah, like think in terms of, say, toluene. The CH3 group of toluene is acidic compared to, say, cyclohexyl methyl cyclohexane, because the same CH3 group, if you deprotonate in methyl cyclohexane, there is no resonance stabilization, but for toluene the CH2 minus can offer resonance stabilization. No, is it clear or not?
Yes, sir.
Yes, sir.
Okay, so we could identify that this is the most acidic hydrogen neighboring to the phenyl that should be involved in the reaction. But see where the new carbon-carbon bond has taken place. The formation has taken place on the opposite side. So if you have like this hydrogen is like more acidic, and if you have an enolate by abstraction of this hydrogen, then there will be a double bond here and this will be a single bond, and then you will get a minus charge here. That should be the more stable enolate, right? That's the thermodynamic enolate. But this time we are generating another enolate by abstracting these hydrogens, where my enolate is, I am redrawing everything, something like this. No, you have a double bond here, a single bond here, and a minus charge here. So that's the kinetic enolate. Can you identify any distinct feature of the reaction which promotes the formation of the kinetic enolate? Steric hindrance is obviously the reason, but I would like you to elaborate a little bit. Can you elaborate on this a little bit? See, this hydrogen is sterically hindered, no?
That was what I
And these hydrogens are relatively less hindered. What is the base that you are using? So is it a sterically demanding base or not? It's a tremendously demanding base as far as the steric size is concerned, and therefore at the expense of the thermodynamic enolate you are getting the kinetic enolate here. And you are also using a phase transfer catalyst, which is tetramethyl ammonium bromide, that facilitates the transport of the reagents from one medium to the other. And you are obviously using as your energy source the microwave irradiation, and you are getting this compound, and see a particular enantiomer is written here with 99% enantiomeric excess. So you have started from one chiral compound and you are getting an enantioselective as well as a diastereoselective reaction, because not only is the chiral center also specific but it also says that this phenyl and this group, they are seen to each other, which means the other diastereoisomers are minor products. So it's a diastereoselective as well as an enantioselective reaction. We are not going to go into the details of why this enantioselectivity, etc. I encountered a question in when I posted the last class's video in YouTube, that we were talking about proline catalyzed reaction, and proline being an organocatalyst with a definite chirality. An asymmetric synthesis was illustrated, and an ex-student of mine was asking this question, that why is this happening. At this point of time, it is not possible for us to venture into those topics. Those will be reserved for future. But we understand at least one thing, that we have a chirality here. This is a chiral center, and therefore our reactions can be enantioselective. In absence of any sort of chirality, we should not expect any sort of enantioselectivity as well. So next time they are doing a reaction with nitromethane in alumina irradiated by microwave, and they have managed to deprotonate this one and add this here, so that in 90% yield they get this compound. Any questions do you have before we move on to the green context? Any questions? Anything bothering you? No?
No, sir.
Okay. So what is the green context? The green context is, with microwave you have definitely renewable energy source. That's like the first thing that should occur to you. High yielding reactions, short reaction time compared to the conventional method, and also you are doing it in a solvent free condition, and therefore disposal of hazardous solvent is not a problem, not a concern for you. So this is a part of a sustainable chemistry. So all of these points are satisfying some of the 12 points of green chemistry, and fortunately for you and for us, most of these reactions have a very common green context. So if you remember 3-4 points, I think you are set for your examination as far as this part is concerned. So we have finished Michael reaction. Let's move on to another famous name reaction, which is benzoin condensation. Do you remember benzoin condensation? কখন পড়েছিলে benzoin? সেম 3 কার্বনিল কেমিস্ট্রি ছিল না? অ্যান্ড benzoin condensation এর তুমি যেটা দেখে অভ্যস্ত, we are going to present it in a little bit different way. Benzoin condensation, if you remember correctly, that it is a cyanide catalyzed reaction of aromatic aldehydes, right?
Yes, sir.
And we are going to end up with a 1,2 bifunctional compound, where oxidation number of one carbon would be on the level of a carbonyl and the other carbon would be level of an alcohol. Okay, so that's a alpha hydroxy carbonyl compound preparation, and that is why it's so valuable. Why is benzoin condensation so valuable? Because we know from our discussions in CEM 4, logic of organic synthesis, that 1,2, 1,4, these bifunctional compounds or bifunctional targets pose a significant synthetic challenge, because those are, remember the term dissonant systems? Do you remember the term? So if you try to disconnect or deconstruct or apply a retrosynthetic analysis to 1,2 or 1,4 bifunctional compounds, invariably, no matter what you do, you are going to end up with an unnatural polarity synthone, and that would require some sort of unpolang or reverse of reactivity. In contrast, 1,3 bifunctional compound, 1,5 bifunctional compounds, they represent a consonant target, and disconnection would lead to normal polarity synthones. We know that the three reactions which are the cornerstone of carbonyl chemistry, excuse me for one moment. Okay, so the three reactions that are the cornerstone of organic chemistry are not organic chemistry, I should say carbonyl chemistry, are aldol condensation, Claisen condensation, and Michael reaction. If you look at the anatomy of aldol and Claisen, both lead to 1,3 bifunctional compounds, and if you take a look at Michael, it leads to 1,5 bifunctional compound. Okay. So what about 1,4 and 1,2? Focusing on 1,2, we have acyloin condensation, benzoin condensation, etc., etc. But those either require radical coupling, like in acyloin, or they require some sort of reversal of reactivity, such as in benzoin condensation. So it's a cyanide catalyzed condensation reaction typically carried out for aromatic aldehydes. Do you know why aliphatic aldehydes are not suitable here? Do you know why aliphatic aldehydes are not suitable? Have you seen aliphatic aldehydes being used in benzoin condensation? No, we have not seen that. But we have seen aldehydes reacting with cyanide, have we not? What happens if you react an aldehyde with a cyanide?
Cyanohydrine.
Yeah, you get cyanohydrine. With aliphatic aldehydes, the reaction actually stops there. With aromatic aldehydes, something much more interesting can happen if you use catalytic amount of potassium cyanide or sodium cyanide. Under refluxing condition, they give this compound which is known as the benzoin thing. Okay. Now we are going to look at it in a catalytic cycle. Okay. Have you seen this sort of catalytic cycle for benzoin condensation before? Where did it go? Here it is. Can you see the catalytic cycle?
Yes, sir.
See what I have written here? So you should start from here. So you get cyanide, okay? And cyanide is a very weird kind of reagent because it has a negative charge on carbon. Generally, you don't get negative charge on carbon. Name me another reagent where you can place a negative charge on carbon. Another reagent. Which also has triple bonds.
Ardent ester reaction.
Yeah, diazomethane, sure, very good. Diazomethane is obviously one example, sure. Another? Carbon has 3 bonds, like triple bond. Any terminal alkyne you can take and deprotonate the terminal alkyne, RC triple bond CH, and then you can deprotonate the carbon by using a suitable base, and therefore you get a negative charge. And also the vast array of the organometallic compounds where we have a carbon bonded with a metal, they represent carbanionic synthones because metal is more electropositive, etc., etc., so on and so forth. But cyanide is also a surrogate for a very valuable functional group. What happens if you hydrolyze RCN? So you get a carboxylic acid, RCOOH, right? So is cyanide not a surrogate for COOH minus? Do you remember that they used to ask this question, that give the corresponding synthetic equivalent of the following synthones? They asked you, yes, COOH minus. So I am talking about something like this. And this is, when I write this in this way, it looks absolutely impossible to get. What should be the, the synthetic equivalent for this one? That's cyanide, because if you hydrolyze it, the cyanide will be hydrolyzed under acidic or in basic condition to give you the carboxylic acid. So this carbon is this carbon, and you definitely have an unusual reactivity there. But coming back to our benzoin condensation, so you have cyanide and you have added like aromatic aldehyde. So what will happen? So this will attack here. Cyanide is a good nucleophile, so it will attack here. Alkoxide, or this can be called the conjugate base of cyanohydrin, is it not?
Yes, sir.
Then what will happen? A proton transfer will take place. Now that's actually that's where the critical step of this whole scheme lies. And this is not a simple abstraction of this proton. It's not like that. We know that this type of rearrangements can happen. They can happen with carbocations, but as you have learned pericyclic chemistry, you know that for anions this type of rearrangement is forbidden in the ground state, and this is a stepwise path. So O minus will pick up a proton from the medium, and from medium something will abstract this hydrogen, but I will get a negative charge on carbon. Why am I getting a negative charge on carbon, and what is the thing that stabilizes that negative charge? Can you tell? What is the stabilizing factor that is responsible for placing a negative charge on carbon? Because we know that carbon does not actually allow for negative charge. For cyanide it's okay, because there is a nitrogen adjacent to it which accommodates the negative charge by minus I effect, so that's okay. But why is the negative charge stable here? What sort of electronic effect the cyanide has? Is it electron withdrawing or is it electron donating?
Electron withdrawing
By minus R effect. So can you see this resonance canonical?
Yes, sir.
And then what happens? You get a negative charge on the carbon. Which carbon? The carbon that was the carbonyl carbon in benzaldehyde. And what was the polarity of this carbon? What was the electronic nature of this carbon in benzaldehyde? Was it electrophilic or nucleophilic? Del plus. That means electrophilic, no? And now you are looking at the same carbon with a negative charge on it and pretty happy about it. So is it not an example of reversal of reactivity?
Yes.
So that's the classic example of reversal of reactivity. In fact, Nikolai Zinin accidentally developed or discovered this benzoin condensation, and it happens to be so Arthur Lapworth was the one who was working on how to find out a reaction mechanism of an organic reaction, and he chose benzoin condensation. So the genesis of organic reaction mechanism was with benzoin condensation. Zinin discovered this reaction 50 years back when before Lapworth started his work. So they had like no idea what is meant by the reversal of reactivity. But now we know that this is a reversal of reactivity. And now looking at this anion, can you tell me why aliphatic aldehydes cannot participate in benzoin condensation? If you had aliphatic aldehyde, then this aromatic ring would not be here. I would have a R group here. Would this carbon ion be stabilized?
So then it will be less stable.
Yeah, sure. Because R is not only electron donating, phenyl can also act as an electron withdrawing group. because if you have a negative charge here, then the negative charge can delocalize itself onto the phenyl ring as well. So I have a minus R effect as well, is it not?
Yes, sir.
So if you add cyanide to aliphatic aldehyde, they just form cyanohydrin and they keep there, no problem. You add a base, the cyanohydrin is collapsed and you get the aldehyde back. But this time you are getting an unusual carbon ion. So coming back to the where is the eraser? Okay, so we have the carbon ion and we also have only a small concentration of this thing because only catalytic amount of cyanide has been added. So lots of unreacted benzaldehyde is present, so this can happen. You get a new carbon-carbon bond. Now look at this oxygen. Is this oxygen closer to the cyano or away from cyano compared to this oxygen?
Away from cyano compared to that.
Sure, cyano has minus I effect, no?
Yes, sir.
So it can stabilize the negative charge closer to it because minus I effect decreases as the distance increases.
Yes, sir.
So if I ask you whether this is a O minus and that is also an O minus, which one is less basic?
So the one near to the cyano.
Sure. So this proton transfer looks pretty okay.
Yes, sir.
Because we know that from strong base we would like to get the weak base.
Yes, sir.
So this it looks okay, the step 4 looks okay, and then what happens? Then just one thing remains. Carbon oxygen double bond is very formidable bond. It likes to form itself back with the ejection of a proper leaving group. Cyanide leaves. Your benzoin is done. Remember this? This is how this thing works. And this is the catalytic cycle that is here. How does it look? এটা দেখতে কেমন লাগে? Pretty neat, huh?
Yes, sir.
I think I collected it from some book. I don't remember. I actually remember part of the name of the author, like 100 Essential Mechanisms in Organic Chemistry. That's a beautiful book. Aesthetically, that is a fantastic looking book, perhaps the best looking organic chemistry book that I have seen, and I have seen quite a lot. So if you have the opportunity of going through that book sometimes, maybe you should entertain yourself, because that's really quite a pleasant experience. And if you are interested to know the roles of cyanide, because CU used to ask this question, I am just recapitulating. So look at the step 1, this is a good nucleophile. Look at step 2, it stabilizes
What is the name of the book?
100 mechanisms in organic chemistry, or essential 100 mechanisms in organic chemistry. I will give you in the group, okay? Just ask me, just remind me, I will share it in the group. And the anion stabilizer effect of the cyano is there, and in the step 5 the cyanide is acting as a good leaving group. So this is our benzoin condensation. Again you may ask that এখানে এইগুলো জিজ্ঞাসা করবে গ্রিন কেমিস্ট্রিতে এসব প্রশ্ন আসবে নাকি? No, I don't think so, but they can ask you this one. What is the disadvantage or the non-green aspect of this conventional reaction? So basically you are using potassium cyanide or sodium cyanide. Not good for you, not good for anybody, extremely poisonous. Handling and storage requires extreme care and use of resources, and protection is required. The cyanide that remains in the medium, the disposal becomes a problem. Where should you put it? If you can't just drain this thing into the water or sewerage, because then the whole thing will be contaminated, and you are doing this reaction under refluxing condition. So if that is done on a heating mantle or anything, or a Bunsen burner or something like that, then you are using non-renewable energy source. how can we make benzoin condensation a little bit green? We can use phase transfer catalyst like a quaternary ammonium cyanide in a two-phase system where you have a organic reagent, organic solvent along with water. See, benzoin condensation has always faced this problem because for certain aldehydes they are not soluble in water, and potassium cyanide or sodium cyanide, they are water soluble compound. So if you are to use a two phase organic system, for benzaldehyde it's not a problem because benzaldehyde is a liquid, but for solid aldehydes, if you need to dissolve it in water where the sodium cyanide is, its hydrophobic part may resist its being soluble in water. It is not soluble in water, its solubility is compromised. So you have to use two phase system where the organic solvent is there, where the aldehyde is, and the sodium cyanide is in the other phase, in the aqueous phase. How do you make sure that they see each other? You use a phase transfer catalyst where you have a tetra-alkyl ammonium salt along with the counter ion is cyanide. Because it has a positively charged cation, it is soluble in water, but at the same time it has large alkyl groups attached to the nitrogen. Those are the hydrophobic part which contribute in making it soluble in the organic phase as well. It can efficiently shuttle between the organic and the aqueous phase and bring cyanide from the organic phase to the aqueous phase to the organic phase. And here they have done this reaction with benzaldehyde, potassium cyanide. They are using water, which is a green solvent, with tetrabutyl ammonium bromide, and within 1 hour they have got benzoin in 70% yield. But if this reaction is done in methanol, in aqueous methanol, you get at 90 degrees centigrade you get excellent yield, but if you do the reaction in water alone at room temperature, the reaction will not take place because of the solubility problem. But you can solve that at room temperature. Within 1 hour you are getting 70% yield, from 0% yield to 70% yield, by using only this compound. So get it? বুঝতে পেরেছো? বোঝা গেছে? Okay. Green context, reaction occurs in presence of green solvent. Method is to some extent time saving. Non-renewable energy sources non-renewable energy source is avoided because the reaction is done in room temperature. Then reaction under ultrasound, fine, another sustainable energy source. Both symmetrical and unsymmetrical benzoin, the cross benzoin condensations can be achieved. Let us look at it. Let us look at this reaction for a bit. We have one substituted benzaldehyde here and the other differently substituted benzaldehyde doing the reaction in DMSO, dimethyl sulfoxide polar aprotic solvent, in presence of potassium cyanide. With using ultrasound we are getting the cross benzoin. But when we are in the domain of cross benzoin, do you remember that not every benzoin condensation is feasible or was found to be feasible? একটা কোশ্চেন আসতো না, এনএন ডাইমিথাইল বেনজালডিহাইড বেনজয়েন কন্ডেনসেশনে পার্টিসিপেট করে না, কেন করে না? অ্যাবসলিউটলি, বিকজ অফ দি NME2, মানে ওটা যদি 4 পজিশনে থাকে, এনএন ডাইমিথাইল বেনজালডিহাইড যেখানে CHO আর NME2 গ্রুপটা 4 পজিশনে আছে, the NME2 group exerts its Plasser effect and therefore it is an excellent donor, but it is a very poor acceptor. When we say donor, we are identifying this part, right? And when we say acceptor, we are identifying that part. Can you tell me how the nomenclature is done? Donor acceptor এটার মানেটা কি? What is donor? See, এই জায়গাটা যদি দেখো, if you look at this part, it has like donated this hydrogen, no?
Yes.
And if you look at that part, this carbon has like accepted this hydrogen. So to act as an acceptor, you have to have electron withdrawing groups present on the ring, and to act as a donor, you have to have electron releasing group present on the ring. Benzaldehyde is placed in such a way in the series that it can act as a moderate donor as well as moderate acceptor. So when self condensation is inflicted, it responds. But for NN-dimethyl benzaldehyde, I am saying the name completely wrong. It should be NN-dimethyl aminobenzaldehyde. NN-dimethyl aminobenzaldehyde, that is a very good donor but very bad acceptor, and therefore self condensation fails. If you take para-nitrobenzaldehyde, then also self condensation fails because it is an excellent acceptor but very poor donor. But if you mix benzaldehyde with any of those two, you will get successful benzoin condensation. If you take the NN-dimethyl version, then it will act as a donor and benzaldehyde will act as an acceptor. And if you take para-nitrobenzaldehyde and mix it with benzaldehyde and do a cross benzoin, then benzaldehyde will be the donor and the nitro compound, nitro substituted benzaldehyde will be the acceptor. Get it? Do you remember these things?
Yes, sir.
Okay, but we have not elaborated on the nature of this R1 and R2, but please make sure that you don't do something where R1 is NMe2 is okay here, but if you take R1 as a NO2, then it's probably not okay, because this part is the donor, and donor should have this R1 should be like what? Electron withdrawing or releasing? What should it be? This is the donor, then this must be K, releasing or withdrawing?
Releasing.
Electron releasing group. And if this part is the acceptor, then what should this part, what should be its nature? In nature kya hoga?
Electron withdrawing.
That's electron withdrawing. So if you are feeling adventurous and if you are writing something on your exam sheet by using specific examples, just make sure that for a cross benzoin reaction you don't mess these things up, because then the examiner would be in a position to deduct some marks. Finally, before ending today's class, we are going to look at one very impressive catalyst that was developed many years after benzoin condensation was in its place, which functions as cyanide. It's a replacement of cyanide. This ring is a thiazole. Okay, remember the 5-membered ring with one nitrogen, aromatic ring, one nitrogen. What was the name of it? Pyrrole. And what was the name of the sulfur analog? Thiophene. What was the name of the ring if you had nitrogen here? Imidazole or imidazole, correct. But this time you have something which is known as thiazole. Azole means presence of nitrogen, and thiazole means both sulfur and nitrogen are present, and they happen to be in 1,3 position. This nitrogen is alkylated, so we called it N-alkyl thiazolium because it has a a positively charged nitrogen on it. Looking at this N-alkyl thiazolium, I am telling you that this hydrogen is particularly acidic. Can you tell me why? Can you tell me why? What is stabilizing the negative charge there? Yeah, that's for sure. Sulfur is more polarizable and therefore it can accommodate the negative, it can stabilize the negative charge adjacent to it, so on and so forth. Also this is like sp2 carbon, and therefore the s character holding up the s character of the orbital that houses the electron is also much higher compared to normal carbon ion. And this is also an example of something which is known as ylide, no? What is the definition of ylide? You have a negatively charged carbon and you have a positively charged heteroatom right next to that carbon. Only one condition has to be met, that the heteroatom which has a positive charge does not have any hydrogen on it. Where have you seen ylides? Name two reactions where you have seen ylides. Korey-Tchaikovsky, where like we had Me2S plus CH2 minus, that's the sulfur ylide. And in Wittig reaction, the more famous ylide reaction involving ylide is Wittig reaction. What did you have? Phosphorus ylide, right? PH3P plus CH2 minus. So no hydrogen on either sulfur or phosphorus is allowed. That's not an ylide. If that happens, that's not an ylide. And so this is an ylide which resembles the cyanide in such a way that it can function all the three roles of cyanide that we have outlined before in discussing the mechanism or catalytic cycle of the benzoin condensation. So Ronald Breslow came up with this N-alkyl thiazolium idea, and he executed this and performed benzoin condensation remarkably, even with aliphatic aldehydes. See, cyanide the aliphatic aldehyde the reaction hoy na base হিসেবে কি ইউজ করেছে দেখো, ট্রাইইথাইলামিন. It is a very very mild base, therefore this hydrogen is very acidic. The electron withdrawing capacity and the stabilization of the negative charge is such that you don't require the presence of this aromatic ring here to stabilize the negative charge. Breslow continued his work and he was actually investigating the mechanism of action of the coenzyme thiamine pyrophosphate, which is also known as vitamin B1, and this is the structure of the thiamine pyrophosphate, vitamin B1. Can you see the N-alkyl thiazolium part?
Yes.
And he further extended it, did an intramolecular benzoin type condensation, and that too using DBU as a base, which is a sterically hindered base. And this time he was not using thiazole but a different heterocycle, but again this hydrogen is similarly acidic. Look at this, this is a chiral center, no? These are two chiral centers, no? So using chiral catalyst, he has closed down the ring, forming negative charge here, attacking here, and see, with great enantioselectivity. And there are further observations, like if you add lithium chloride, like inorganic salts like lithium chloride, then the reaction is faster. In presence of cyclodextrin, gamma cyclodextrin also accelerates the reaction, but beta cyclodextrin inhibits the condensation. But those are advanced topics, let's not go into those things anymore. So what is the green context? The first green context is that you are avoiding cyanide, which is very bad for your health, and people working around you, extremely poisonous reagent, that is avoided. Waste treatment is very simple, you don't have cyanide, so you don't have to worry about its disposal. Reaction occurs in low temperature in short time, method is safe, cost effective and eco-friendly. So pretty much a win-win situation for everybody. Anybody has any questions on the benzoin condensation or N-alkyl thiazonium, etc.? Because in the next class we will be starting a brand new reaction, Dickman condensation. Not brand new, you know this thing, but new in this class, at least the green aspects of it. কারো কোনো প্রশ্ন আছে কি?
No, sir.
ওকে, তাহলে আমি রেকর্ডিং বন্ধ করে দিই।